www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
So let me get started. So this is lecture 19 on numerical solution of transport equations. As I have mentioned to you already, that there are essentially this 3 or 5 transport equation depending how you count it. One is Poisson equation, 2 continuity equation, and each continuity equation is complemented by this drift and diffusion component, these 5 equations. And in the last class, we discussed how to solve the problem analytically. If you remember the Schrodinger equation solution of it, we did it in 2 ways. One is analytically with sine x and cosine x, or e to the power alpha x, e to the power minus alpha x. We did that, matched the boundary conditions and solved that. And in many cases, as I said, it's very useful to be able to approximate the problem and solve it quickly in the back of the envelope in 5 minutes. And that is how historically it has been done before the days of computer. But fortunately or unfortunately, we have big computers today, and that allows us to solve the problem with very little approximation. And as a modern student, now, it will not be appropriate if you don't learn a little bit about how the numerical solutions of these equations proceed, and you actually have already been using it through NanoHub. So I want to understand, well, I want to show you what is the machinery behind the program that does your calculation. When you hit return on a problem, it does a bunch of things. You see a number rolls down on your screen, and then it's trying to do something, and eventually it gives you a result. What is it doing in the background? It is actually solving those 5 equations, and I'll try to give you a flavor of it. I cannot do a full justice, a flavor of it, that what's going on in the background. I'll talk about grading and finite differences, talk about how to discretize equations and apply boundary conditions, very similar to the Schrodinger equation, very similar. So you will see many similarities between these two, and then I'll conclude. The reference, this is not here any book that I can refer to, but Professor Lundstrom has a primer on semiconductor device simulation on nanohub.org. You can take a look. Many of those features, I have simplified it, but essentially it comes from there. So you remember, the first equation is the Poisson equation, and we'll show that a graphical solution of this is called drawing a band diagram. You see people are saying, can you draw me a band diagram of you have invented a new device, let's say, and somebody says, can you draw me a band diagram? Let me see whether it works. He's asking you to solve the Poisson equation, and you can do it in 5 minutes, easy, less than 5 minutes, for any problem whatsoever. And then there will be a bunch of equations, continuity equations for electrons and holes, and we will solve it in various approximations. And in the last class, we already solved a problem, if you remember, in the diffusion approximation, where drift was not important, right? The electric field was very small. And then we also involved minority carrier transport, because it was a small perturbation on the majority p-doped material, a few electrons there. And we tried to solve that problem. That allowed us to simplify the recombination term. If it were lots of carriers, we couldn't do the simplification of the recombination term that we did last time. So we are already doing it. I'll also show you how to do ambipolar transport when both electron and hole numbers are comparable. So in that case, the approximations that we made in last class doesn't really hold. And I will show you later on how to handle those cases also. But today, my goal is not analytical solution, but to solve the numerical solution of this problem. Now, generally people write it in 2 sets of equations. One is that they write conservation laws, conservation of fluxes. As the first thing is the Poisson equation. And the second and the third is the continuity equation. What's the difference between this continuity equation and the one that was in the previous slide? Do you see? This is steady state. I'm simplifying it. There's no d and dt term that I have written here. So steady state, you remember, right? All the fluxes essentially balance each other. So no net charge change in net charge in any given volume. So I have just done a simple thing because transient involves a little bit more complexity. So I want to avoid that. And then, of course, you talk about the various relationship where physics comes in. The left-hand side, you can write it 2000 years ago. I mean, there's nothing fundamental about it. Flux coming in, flux getting out. It could be water, it could be, it could be electrons, it could be anything from the left-hand side. The right-hand side is where physics comes in. Because right-hand side, you have to find an expression for P and N. You have to learn about drift and diffusion, and in the diffusion coefficient and then the mobility, you will have to know about this effective masses and the scattering time. That is where all the physics is hiding in the right-hand side. The left-hand side are general conservations law. So let's try to see how to solve this problem on a computer. And the generation recombination is just another term. Okay. Now, how do you solve it? The first thing is, what do I solve? What do I solve? What is the unknowns in these equations? Now, do you see what the unknowns could be? First of all, there's 3 equations, and there are actually just 3 unknowns. What are the unknowns? Electron concentration, hole concentration, and electric field or potential. Either one would be fine. Electric field or potential. These 3 things. Do you agree? The first one, the Poisson equation, involves electric field on the left-hand side. On the right-hand side, it involves electron and hole concentration. So those are two unknowns. The second equation, electron concentration, what does it involve? Well, again, electron concentration, of course, the continuity equation, that's right. But what about the recombination generation? That involves electron not stuck to the holes. So that equation involves holes. And also the drift term and the diffusion term, that involves the electric field component of it also, right? So therefore, you can see that there are essentially 3 equations and 3 unknowns. And the 3 unknowns are potential, electron and hole concentration, but not just 3, 3 at every point. And if you have a lots of points within the device, then it will be, concentration will be going up and down. And so at every point, you will have a corresponding solution at the end of the day. So we'll try to see how to calculate these numbers in a general way, in a simple way. And many of you may already have seen it in different contexts. Why is it coupled? Because you can see the first Poisson equation, the solution of that will give me the electric field. But the electric field now determines the current. But as soon as it determines the current, you can see it sloshes around the electron and hole concentration. That changes the Poisson equation. So these have to be solved in a coupled way until we have a self-consistent solution everywhere. This I have mentioned, and I want to emphasize it again because many of the equations that you will be learning may not apply in your research career, in the sense that the conservation laws will always remain with you. 50 years from now, at the end of your research career, maybe it will stay with you. But the transport equations, you will see, this is already changing in a significant way. Professor Mark Lundström talks about ballistic transport when there is no scattering. Professor Supriya Datta talks about when quantum interference is very important at every point. So we work on random material, transport through random material, where many of the assumptions fail, and therefore the transport equation will change. The drift and diffusion, the form of it will change, but the conservation law will always remain the same, hopefully. Now let's talk about grading and finite differences. So how do I do that? Same way I did it in the Poisson equation, Schrödinger equation, the same mechanics, same way. So what should I do? Let me take a device that 2 sides on the left and the right side, let me assume those are contacts, meaning that is where I will attach my battery. So on one side may be grounded, connected to 0 potential. the other side of the potential, depending on whether it's a plus voltage or minus voltage, it will be at various potentials. Now, in between, I do not know how the potential varies. I do not know how the electron concentration varies. That's something I will have to find out. So the first job is to grade it. Grade it meaning connect the first and the last point between the two contacts and essentially divide it into many segments. Now here I have drawn each segment to be the same. This is called uniform grading. Uniform grading essentially allows this region to be segmented in uniform sections, but it need not be uniform. In fact, the problems that you are solving in your computer for this homework, if you just tried uniform grading, it would have been too big a problem many times to solve the problem accurately. So many times non-uniform grading is essential for practical solution. But for conceptual reasons, here I will just assume this to be uniform. What is this A? A is not atomic dimension. It's not 5 angstrom. It depends on the problem. If your whole thing is about 100 micron, let's say, then you would probably grade it maybe in 100 small segments or maybe 200 small segments. So a micron or a tenth of a micron, that would be typical size, so that you can use effective mass at every point. If you try to grade it on the atomic scale, of course the notion of effective mass is not there anymore. So you shouldn't try to do that. You should grade it a little bit bigger in size. Okay. Now every point I will mark it as I, node I, and node I has an unknown V sub I is the potential at that point. N sub I and P sub I are electron and hole concentration at that point. And in the beginning, these are all unknowns. Every point I do not actually know anything about this. Only thing I know is on the boundaries I have attached a battery of a given voltage. So V sub 0 I know because that's the battery. And V sub N or N plus 1 on the other side, that I know because that point is grounded. Apart from these two information, I know nothing. At the end of the day, I should be able to calculate all this through the help of the three equations we talked about. So in order to do that, I need an approximation, just like we did it in the Schrodinger equation, an approximation for the first derivative and numerical approximation for the first derivative and the second derivative. And this you know, so this you may have seen many times. So let's say I have a grid point at x, ith grid point at xi, and the I plus 1th grid point at xi plus 1, right? Let me take the middle point. And let me try to see what is the derivative of any function at that midpoint between xi and xi plus 1. Now fx, what is that? Eventually it could be potential, it could be electron concentration or hole concentration. It's a generic representation for fx. How do you do a derivative of this sort? Very, very easy. So you write it again in the Taylor series. You write that f at x naught being the middle point, let's say, that is x naught plus a plus 2, right? The value on this right, on the magenta, the color is not coordinated, I see, but you can see minus a over 2 df dx, right? Because you want to know how much is a little bit before that point, the first derivative, you know. And correspondingly, the red one, you can correspondingly write x plus a, which is at xi plus 1. Do you see that? And then it will be derivative multiplied by a over 2 because it's half the distance, right? So now if I subtract these two things, two quantities, then what will happen? Do you realize that if I subtract, the magenta will go and the blue and the red, I will write it as xi and I plus 1. You see that? And there is a plus a divided by 2. After subtraction, that becomes a. So that's a is sitting on the denominator. So the slope of the function at the middle point, why in the middle point I'm coming in a few minutes, but in the middle point is given by this function. If I know the two node point solutions, which I don't, but if I knew, then I could calculate the derivative easily. What about the second derivative? Now this I have copied from the Schrodinger equation, you can see, so I shouldn't have to explain too much. I say that at node xi plus 1, that's the value, right? Taylor series expansion. and at x I minus 1, that's the value in the equation on the second one. What do I do here? Do I subtract? Not really. If I want the second derivative, then I simply add. And when I add this, I get the second derivative because the first derivative drops out. Now, the one that I wrote in the previous slide, and this one is the same expression actually. In the previous slide, I simply didn't carry around the second derivative term, the a squared term. But other than that, it's the same thing. So when you add this, you can get an expression for the second derivative. And then you write it in terms of functions at 3 node points. Second derivative, of course, you should know it's like a parabola going through 3 points. So you have to know about 3 points. Now the thing is that this is called a 3-point formula, right? Now there are higher order discretization also in 1D even that will give you 5-point formula, 9-point formula. If you go in Google and search finite difference, they will give you the list of formulas. But this is the simplest 3-point formula that we will be using. And this is what is also in your device simulator that you are using on the NanoHub. All 3 based on 3-point formula in 1D and 5-point formula in 2D. Because you can see 2D will involve 2 side points and top and bottom. So that will give you 5 points, 5-point formula. Okay, so I have the discretization of the functions. Let me see whether I can discretize the equations, the drift diffusion equations properly. So 3 unknowns at each node, and I need 3 equations each node then. Therefore, I can connect them all up. How do I do that? So the first thing is, of the long chain between the 2 contacts, I have just focused on one grid point, the ith grid point. Then I could be anything. I could be 5, for example, the 5th grid point, and I'm focusing on the 2 neighboring points, I minus 1 and I plus 1, and I have divided this segment into I have bisected the difference. It's just like, what was this algorithm called? Wigner-Site algorithm, do you remember? That if you bisect it is 2 points in the midpoint, so this is what I have done. So that's why I wanted to know the derivative at the midpoint, because that will help me. And this volume here in numerical discretization is called a control volume. Control volume, essentially, you just focus on this, write all the equations for one node, and essentially just copy and paste for every other node. Then you are done. So let's start with the Poisson equation. Now, the left-hand side, I have written the Poisson equation being the second derivative of the potential, and you should notice with a minus sign. Where does this equation come from? I have not been writing the equation in this form until now, but you can easily see from the extra equation that I have within the box that where it comes from. I was generally writing it in terms of displacement D. So divergence of displacement D, I said that that's equal to the charge rho, but the displacement is proportional to the electric field, right? Up to the dielectric constant. So that you can see the displacement, I can write it in terms of the electric field, but the electric field is minus of the gradient of the potential, right? So therefore, you can see that if I insert the expression for the displacement, then I will get a second derivative of the potential with a negative sign. That is where that equation came from. Same Poisson equation. Okay, and then, so how am I going to discretize this equation? Now, in many ways, this looks like almost like a Schrodinger equation. Do you see that? Instead of V, if I had a psi, then it almost looks like a Schrodinger equation. So it should be, the discretization should be very similar. There's no complicated thing here. So let's try to write it. Do you agree with this statement? The first term is a second derivative. I'm solving a one-dimensional problem, and in the one-dimensional problem, the divergence of this nabla square, that will be equal to essentially second derivative of with respect to the position. And then in the previous slide, I already told you that if I knew a function f, I wanted to calculate the second derivative, that should be the expression on the left-hand side. So no problem, right? I need to know the potential at I and the 2 neighboring points, I minus 1 and I plus 1. I don't know them yet, but that's what I need. What about the right-hand side? Do you agree with this statement? So in the right-hand side, I have Q and the dielectric constant, that's fine. But I also have the electron and hole concentration, but at node I, right? Node I, because this is what I am thinking about. And similarly, the doping concentration at that node. Now, if you have a uniform semiconductor, then the right-hand side will always be the same. However, if you have part of the region N-type, part of the region, let's say P-type, then you can see in some of the grids, you will carry one type or the other type, ND or NA, but not both of them, let's say. And so you can just throw it in this one. This is given already, and the unknowns are V, Pi, P sub I, and N sub I. That's the information. In general, if you wanted to write this whole equation in terms of some compact form, you could say that the Poisson equation essentially is a function of three potentials at three neighboring node points and the carrier concentration at that node point. So this is just writing the previous equation in a compact form, essentially looking at the functional dependence. Okay, so I have one equation. So if somebody gave me Pi and Ni at every point, I can solve this equation, right? Can I? Because on one side, I know potential is 0. And on another side, I know the potential is equal to the battery voltage. And then each three, I keep connecting them up. So just like the Schrodinger equation, I can solve for the potential. So that will be the solution of the numerical solution of the Poisson equation. Now, what about the current equation? Well, that's a little bit more tricky, but not too much. Let's see how it works. So I will have to do dJ and dx, right, the electron current, and then there is this generation and recombination terms. That's fine. And I have already, I know that the carrier concentration current is given by the drift term and diffusion term. Do you recognize the first term as drift? Because it was Q n mu n electric field E. I have just written it as minus dV dx. So that's the electric field. And the second term, do you recognize where that came from? Well, I have used Einstein's relationship to replace d sub n, the diffusion coefficient. Why? D over mu is kT over q. I always say it rhymes, right? So that's how you should remember. So you can see that's why I have replaced it with kT mu n and dn dx. That's the gradient. That's the gradient. Okay. So how do I represent this current? Again, not too difficult. I have divided both sides with kT mu n, and so you can see that how it works. But in terms of the value n, which is in magenta, how do I know value at a given point? Well, I can take the average of the neighboring 2 points, ni minus 1 plus ni divided by 2. Now you could say, why shouldn't I take average of the other two? Ni plus 1 plus ni divided by 2. You could do that, no problem. It will give you the same answer at the end of the day. What about dV dx? The dV dx, do you recognize that the first derivative we just derived a few slides ago, df dx, that gives you dV dx between these 2 points. And now you also realize why I took the derivative at the midpoint, because that allows me to get the derivative in terms of the functions, known functions at I and I plus 1. Okay? So this is the first term, and correspondingly the derivative term dn dx, it is simple, the same thing. And so you get this j and insert it in the first equation, then that gives you a corresponding equation that you can solve. And at the end, I didn't do that step, but just to give you a flavor, then you can see, do you agree with this statement that this continuity equation will actually depend on all the potential? Where is the potential coming from? From the drift term. That's all the potential and carrier concentration throughout this region for this node. And so therefore, you can solve this equation that will give you the carrier concentration at every point. If somebody gave you the V and P, let's say the whole concentration, then you could easily calculate the electron concentration on its own. So the minority carrier diffusion that we did in the last class, we didn't solve for the Poisson equation, right? Do you remember? We didn't, because we said the electric field is 0. So in that case, the potential was sort of given, right? And the whole concentration was very large and uniform. So we didn't worry about that one either. We just solved for the electron continuity equation. So this is why what we are actually solving in a simplified form. Okay, so this is electron continuity equation. And you can correspondingly do a whole continuity equation and you are done. So you can see the 3 unknowns at each node, and if your device has 100 nodes, how many equations do you have? You have 300 equations, because each node connects to the neighbors, and the first and the last one are special because that only connects to the one side. But other than that, you have about 3 times the equation that you have to solve in a coupled way. Okay. This is nonlinear in the sense that these are coupled. This solutions, one solution depends on other one, and in that sense you cannot solve them in a decoupled way, an individual way. So what is done in the computer is, at the end of the day, if you just wanted to solve Poisson equation, you will just do it in the same way we did it for the Schrodinger equation. You will discretize it and put it in the matrix. It will essentially be just banded matrix connecting the neighbors. So therefore, I have drawn essentially the 3 lines, and then the potential at every node, V1, V2, V3, Vn, these will be the solution coming out. V1 and Vn are known from the known boundary condition. So one can solve this. Maybe I should assign a homework problem for you to write this code so that you'll really understand. Okay, now the boundary condition is very important. I told you about the potential boundary condition, that's easy. But the boundary condition which are a little bit tricky are the electron and hole boundary condition, but you already know that, how to handle this one. Potential boundary condition, I write it here, no problem. Now when you want to write the boundary conditions for the electrons and holes, you have to assume, and this is a fundamental assumption, that electrons and holes are always in equilibrium. Device may be in non-equilibrium, electron hole sloshing around, potential going from one point to another, but the 2 contacts, these always has to be in equilibrium. Now if it is in equilibrium, what is the relationship it must follow? It must follow N naught multiplied by P naught is equal to Ni squared. Do you remember this? This is the detailed balance, right? Law of mass action, and it of course comes from the detailed balance also. Now if that contact is in the P region, then what is the value of P naught? That is equal to Na, right? Whatever is the doping at that point, and from that you can immediately get the value of N naught, right? So that in the boundary, by assuming that relationship, you immediately know the value of N naught and P naught, but only at the contact. Same thing on the other contact also. Same thing on the other contact, because that contact is also in equilibrium. And as a result, again the multiplication of the 2 is Ni squared. And as a result, as soon as you know the majority carrier concentration from the doping, then you immediately know the minority carrier concentration from this relationship, and then you put them in. That's the boundary condition for electrons on one side, boundary conditions for electron on the other side, and in between this differential equation connects them up, right? So that's the solution. Now remember, in general, although I have written Ni squared in both cases, if one side is gallium arsenide and another side is aluminum gallium arsenide, like there are transistors that have this type of things, then is the Ni squared same on the both sides? Obviously not, because Ni squared is N, capital N sub C, N sub V, and band exponential of the band gap. And different material has different band gap, a different effective density of state. As a result, this number on both sides need not be the same. That's a material dependent parameter. Okay, but once you have this on the 2 sides, and once you have the potential, then you can solve everything inside. So So the equation you are solving every time you're hitting that key in NanoHub is it is going in and internally solving this humongous equation. But it's really not humongous. You can see this in the following way. You see the vector that is multiplying the whole unknown. The unknown, this matrix contains all the mobility terms, the discretization, the A terms, everything that's multiplying Vi and Vi minus 1. All this is inside the matrix. I have three equations, so I have a n continuity equation, the whole continuity equation, and the Poisson equation. And this vector starts from x1 to xm, first point to the last point. And similarly, the unknowns are p to pm and potential from the first point to the last point. And this is what I'm trying to solve for. And that's the boundary condition I just told you about, right? N naught you got how? N naught multiplied by P naught is Ni squared. So that's how you knew that N naught. And similarly on this side, the boundary condition I just told you about. So that one is from the other contact. And so on the right hand side, you will have these terms sitting in there. And similarly, you can do for the holes at various points. Again, the boundary conditions I just told you about. And you can do it for the potential, and the boundary conditions are again from the two contacts. And so that's the right hand side is the boundary conditions. These are bunch of unknowns. Now, do you remember that when you simulated for the homework that a column of numbers comes through? There's the first column of numbers, second column of number, third column of number coming through. Did you remember to see this? So that numbers is solving the n. After finishing the solution of n, solving the p, and then inserting this information of n and v in, and solving the p and solving the v. So you will see an n written on the top of the column, a p written on the top of the column, and a v written on the top of the column as they swing through your screen. So next time you do it, pay notice that that is actually what you are doing. Now this one, so this one is a potential, that's fine. But you see this column, this grid, this box, what does it represent? This one represents how the Poisson equation talks to, am I doing something wrong? This one gets multiplied this with the Poisson equation. I'm sorry, I should have put it in here. So essentially, because Poisson equation talks to the number of electrons and number of holes that it needs, right? So it should have talked to the continuity equation. That's where the solution would have been coming from, and correspondingly to the electron concentration. So there is this two off diagonal component that it has to talk to from the continuity equation of n and p. And similarly, there are these terms. These are because of recombination generation. Because only when you have recombination generation, the electron needs to talk to the holes. And so therefore, the n continuity equation will need to talk to the p continuity equation to get the whole concentration. So that's on off diagonal term. If you don't have any recombination, then you will not have that term. And similarly, for the electrons likewise, there will be a corresponding term for the recombination, because anytime one electron disappears, a hole disappears, right? So anytime you make one electron disappear from one of the columns, there will be a corresponding hole disappearing from the respective other column. And so therefore, this cross term takes care of any recombination you have. If you don't have any recombination, then essentially it will be diagonal, except that the potential equation will couple the electron and hole concentrations. But apart from that, it will essentially be decoupled. So the general way that you start solving it is you start on the right hand side, focus on the right hand side of the column of information. So you'll start by guessing a potential for V, N, and P at every node points. You will solve the Poisson equation assuming electron and hole concentrations are kept fixed. Once you solve the Poisson equation, you will get that drift term, and correspondingly you will solve for the electron concentration, and from assuming the hole concentration and potential are fixed, and that gives you the electron concentration, and similarly the hole concentration, and you will keep doing it. You see, that's why we don't do it on in pencil and paper. The computer doesn't mind. It can go around doing it, and until everything is satisfied, and you have a full solution. Okay, so that's about it for the numerical solution. I will not be asking any detailed question about this, but I want, as a graduate student, you to appreciate the complexity that goes behind it, and that's what every time you solve a problem, actually a lot of things happening behind your back, and understanding this physics is very important so that you don't make a mistake while you are doing a numerical simulation. So the summary is that we said two methods of solving drift diffusion equation, analytical and numerical. I gave you one example for analytical, and throughout the rest of the course, we'll give you many more examples under various conditions how to make approximations. But the numerical one is general. Numerical one, it doesn't care about approximation. So once you can give it a proper problem, it will solve it for you. It may take time, but it may not converge even if you don't do it right. But otherwise, it is a general thing that doesn't make any approximation here. Now, I want to emphasize that the analytical solution provides insight. Numerical solution, it is like trying to drive a car. That even when you don't know anything about the machinery of the car or the physics of the car or how it works, you can still drive a car. And many people, if you teach them a little bit, technicians and others, many times in companies, they can do this, run this. But if you want to design a new device, if you want electrons to go in a certain way, in a certain place, numerical simulation will not tell you that. That you have to do it in your head with analytical solutions and sort of thinking about that. If I do this, what happens? You should know that answer in your heart in some way, and that is the only way to be an engineer. Learning how to run big programs doesn't make you an engineer, right? Okay. And numerical solutions, of course, once you know how to use it, it's more versatile. That even when you cannot see the solution on a piece of paper, most of the time you can start with numerical solution in that case. And once you look at the solution, then you can develop back your intuition over a period of time. So it goes back and forth. It should be done. It should be done in both ways. So you got a flavor of this. Okay.